Example 3 is a bit challenging, so let's take a look at it. The world's worst nuclear accident occurred in Chernobyl, Ukraine on April 26, 1986. Immediately afterward, 28 people died from acute radiation sickness. So far, about 25,000 people have died from the accident, mostly due to the release of radioactive element cesium-137. Cesium-137 has a half-life, of 30 years. Again, what half-life means is if you had 100% at the time of the accident, after 30 years, half of that remains. So therefore, after 30 years, 50% remains. And then after another 30 years, half of that 50 remains, which would be 25%. So after 60 years, a quarter remains. So let's continue. Let P equal F of T be the percent of cesium-137 that remains T years since 1986. Find the equation of F. Again, we need the initial amount and we need the base multiplier. This is just a little tricky. It doesn't really say how much you started out with, but because it's radiation, you start out with full radiation, 100% of cesium-137 initially. And so I will use the number 100 representing 100%. The base multiplier, as you might have guessed, is 1/2 because it has a half-life of 30 years. However, I cannot just put T here, because if I put a T there, then after year 1, we get half of the 100%, which would give us 50. When I put 30 in, that's supposed to give me 50. So what I will have to do is divide this by 30. Now when I put 30 in for T, 30 divided by 30 is 1, so 1/2 raised to the 1 is 1/2 times 100 would give you half, or 50%. So that is one form of the equation, and I will give you almost full credit, but partial credit for that equation. I want you to simplify it so that the exponent only has a T. To do this, I'll do a little hocus pocus here. We'll use the properties of exponents. Notice that with exponents, I'm going to want the T on the very outside. And notice with exponents, if I raise a power to a power, I multiply. Well, if I were to multiply these two numbers, I have to get T over 30, so this would have to be 1 over 30. Well, if that's one, notice that when I multiply these together, I do get the original equation. Well, now I can calculate, instead of 1/2 raised to the 1/30th, I can calculate what that is each year, the decay or the multiplier for each year. Let's take a look at our calculator. And if I did 1/2, which I'll just do it the long way, 1 divided by 2 raised to the 1/30th, which would be in parentheses again, 1 divided by 30, I end up with this number right here. And that's our base multiplier for each year. So it's not going to go down half each year. It's going to go down, basically, it looks like 2.3% approximately. Let's round that number to 3 decimals, and that would be 0.97. So that would be the same thing as 100. So this raised to this is 0.977. And now there's an equation of T, where T is each year. Let's double check it by simply doing this. Let's put in 30 and make sure we get the right answer. Well, you know what? We're going to be doing problem 3, so let's put the equation in y equals here real quick so that I don't have to keep entering that. So we have 100 times 0.977 raised to the T. Enter. And I'm going to go into table, and I'm just going to hit delete a whole bunch of times to clear all these out. So notice if I put in 30, I do get that there's about half as much. 49.755 is almost 50%. Let's put a 60 in, and notice I get about a quarter, which we guessed as well. So 2 says describe the meaning of the base of F. Well, this is just how fast that the radioactive material decays each year. 3. What percent will remain in 2014? Well, let's see. This happened in, I'll have to move my calculator, in 1986. So 2014 minus 1986, running out of paper, gives us 8. I'm under pressure. 28 years. So rather than going and doing that, I can just plug in 28 right here. And notice I get 52.125. So I'll just put approximately for number 3. Approximately 52% would remain in that year. So there you have example 3.